I'm going to discuss about irreversibility and heat generation in the computing process. So there are computing machines which involve devices performing logical functions that do not have a single valued inverse. This logical irreversibility is associated with physical irreversibility and requires minimal heat generation per machine cycle, typically of the order kT for each irreversible function. This report contains the discussion on various characteristics associated with these processes and what are the possible errors in the same. So this is the bistable potential well, as you can see, and this is the potential well in which 0 and 1 state are not separated by the barrier. So let us arbitrarily label the particle in left and right hand well in 0 and 1 state. Now consider the operation restore to 1, which lower the particle in one state regardless of its initial location. If we are told that particle is in the one state without spending energy, if on the other hand we are told that the particle is in the zero state, we can apply a force to it which will push it over the barrier, and then when it has passed the maximum we can apply a retarding force, so that when particle arrives at 1 it will have no excess kinetic energy and will not have expended any energy in the whole process, since we have extracted energy from the particle in its downhill motion. Thus, at first sight, it seems possible to restore to 1 without any expenditure of energy. Note, however, that in order to avoid energy expenditure, we have used two different routines depending on initial state of device. This is not how a computer operates. In most instances, a computer pushes information around in a manner that is independent of the exact data which are being handled, and in only a function of the physical circuit connections. Reverting to the original direction of the time development, we see then that it is not possible to invent a single FT which causes the particle to arrive at 1 regardless of its initial state. Classification. The simplest class and the one to which all the arguments of subsequent section will be addressed consists of devices which can hold information without dissipating energy. The second class of devices consists of structure which are in a steady time invariant state but in a dissipated one while holding onto information. The third category belongs to von Neumann scheme, which we shall not attempt to describe here in complete detail. One uses a pump signal of frequency omega naught, which when applied to a circuit tuned to omega naught containing a non-linear reactance will cause the spontaneous buildup of signal at the lower frequency. Logic in irreversibility. We shall call a device logically irreversible if the output of a device does not uniquely define the inputs. We believe that devices exhibiting logical irreversibility are essential to computing. Logical irreversibility, we believe in term, implies physical irreversibility, and the latter is accompanied by dissipative effects. We shall then think of a computer as a distinctly finite array of n binary elements which can hold information without dissipation. Reversible computing. The reversible computer can utilize only those truth values whose truth table exhibiting equal number of ones and zeros. The machine must therefore have a great deal of extra capacity to store both extra bias bits and the extra outputs. Also, in order to provide space for extra inputs and outputs, the embedding requires knowledge of the number of times each of the operation of the original machine will be required. The usefulness of a computer stems, however, from the fact that it is more than just a table lookup device. It can do many programs which were not anticipated in full detail by designer. Entropy. An assembly of ordered bits would act in a similar manner as the assembly thermalizes and forgets its initial state. The environment would be cooled off. So entropy is given by K log EW. It will vary to zero entropy. The degree of freedom associated with the information can through thermal relaxation go to any of the 2 to n states n bits in the if there are n bits in assembly, and therefore the entropy can increase by kn log 2 factor as initial information becomes thermalized. However, for each possible physical state which will be interpreted as 0, there is very similar possible physical state in which the physical system represents a 1. If these are all reset to 1, the number of states covered in the ensemble has been cut in half. The entropy therefore has been reduced by k log 2, which is 0.693 times k per bit. The entropy of a closed system, example a computer with its own batteries, cannot decrease. Hence this entropy must appear elsewhere as a heating effect supplying 0.693 kt per restored bit to surroundings.